So now that we've kind of looked into how we can determine different discontinuities from limits and kind of the different cases for these discontinuities in general, and I mean, we kind of came to these three conclusions over here. We said that, in general, if, the total limit won't exist if, first of all, the single-sided limits don't agree with each other, then in general we can assume that there's going to be a jump discontinuity. Or if the total limit is given, by direct substitution is given by some non-zero value divided by 0, and in this case we assume that we would have a vertical asymptote. And if by direct substitution the total limit is given by 0 over 0, which is an indeterminate form over here, then we assumed in general that we're going to have a removable or a point discontinuity. And so what we're going to do in this video is we're going to actually kind of look at how, certain limits at points that are undefined. So you may have an asymptote, or you may have, maybe a point discontinuity, a jump discontinuity, or something. At points that are undefined, how we can still determine a limit by kind of approximation, by taking values that approach that particular a value, inputting it into the function, and kind of seeing from both directions what we seem to be approaching, if anything. And so let's actually take a look at these particular examples over here. So we have, right over here, we have the limit as x approaches 0 of some arbitrary function f of x. And they didn't give us the equation of f of x, but they gave us this table over here. And what's good about this table is they gave us, in this portion over here, they gave us values of x that are less than 0, but are very close to 0. They're approaching 0. However, they are just barely less than 0, so we can say these are less than 0. And then over here in this portion, they gave us values that are greater than 0. I mean, they're just barely greater than 0, but we can see we are approaching 0 from both directions. Our x value is approaching 0 from both directions. And then right down the center, we have f of 0 is undefined. So at x equals 0, we have that the function is undefined. So we can't use direct substitution in this particular case to evaluate the limit. Instead, what we can do, though, is we can use kind of our knowledge of single-sided limits. So we can think about the single-sided limits right over here. So let's first think about values that are less than 0 of f of x. And then we can think about values that are greater than 0. And what we can do is we can look at these single-sided limits and we can approximate them from the table. We can just kind of make sort of an inference. We can see what the function seems to be approaching as x approaches, these limits from, or these single-sided limits. We can kind of look at that and see if these two are equal to each other. If these single-sided limits are equal to each other, then we can assume that the total limit is going to be equal to whatever that value is. So let's actually go ahead and do that. So we see over here, we have these very kind of small step sizes. We have negative 0.1, negative 0.001, and then negative 0.00001. And then if we look at the corresponding f of x values, we see 2.9, 2.999, 2.99, etc. And so essentially what we can see over here is as x approaches 0 from values that are just barely less than 0, as x gets closer to 0 from values that are just under 0, we can see that we seem to be kind of, we start with 2.9 and then we seem to be approaching closer and closer to 3, right? We seem to be approaching 2.9 bar, which, would essentially be 3. It seems we're getting closer to that particular value. I don't know why that happened. And so we can assume that this single-sided limit over here is going to be equal to 3, right? And this is just an approximation. This is just an inference based on what we're given in the table, because it's not like we're actually given the equation of the function. We're just given different values at the table. And I mean, if we were actually given the equation of the function, then we could actually just take different values, and we can even approximate values that are even less than this number over here, or well, technically greater than this number over here, but less than 0, and then we can use that as another value to approximate. We can keep doing that and see what happens as this number over here gets even closer to 0. And so we got this single-sided limit equal to 3. And then let's look at the other single-sided limit, the values that are greater than 0. We can see these different step sizes. We have 0.1, 0.001, and then, I don't know why that decimal point's missing there. But yeah, we have this number over here as well. I'm not going to try to read it out. But the point is, we're getting very close to 0 over here. And if we look at the corresponding f of x values, we have, 2.9, 2.999, and then this number over here, it seems to be following the same pattern as the values that were less than 0. And it seems in this case that we're also going to be kind of converging to 3, right? It looks like this limit is just going to be equal to 3. And so now, I mean, we were undefined at x equals 0, so we couldn't use direct substitution. However, we could use the information we were given in the table to kind of see what these single-sided limits were. And these both exist, right? These are just valid limits. They both exist, which is first a very important thing to keep in mind. Exist. And they're also both equal to each other, right? These are equal to each other. And so the single-sided limits, they exist, they're equal to each other, and so we can say that the total limit is just going to be equal to 3 in this case. And so, we were undefined at x equals 0, however, we can still determine a limit using this information. This next example over here, we're going to use the same logic. We can look at the limit, so we're taking the limit of g of x as x approaches 2, so we can look at the single-sided limits, so from values that are less than 2 of g of x, and then from values that are greater than 2. From 2 of g of x, right? And then we can, again, same logic, we have these right over here are the values that are going to be less than 2. This right over here is values that are greater than 2, and then this is at x equals 2. The first thing to do is check if it's actually defined at x equals 2. It seems like we're not defined at x equals 2 in this case. And essentially, we can then just kind of look at the different step sizes. We can see, we have 1.9, 1.999, etc., and we can look at the corresponding g of x values. So we have 6.1, 6.001, and then this number over here. So it seems, from the values that are less than 2, as we approach 2, from values that are just barely underneath 2, we seem to be approaching, 6, right? This looks like it's going to converge to 6. As we can see, this is getting closer and closer to 6 as we approach x equals 2, from values that are less than 2. And then if we want to look at the other direction, if we want to look at the other single-sided limit, we'll have, 2.1, 2.001, and then this number over here. And the corresponding g of x values seem to be a little bit interesting in this case. We have negative 4.9 and then negative 4.999, and then this number over here, which is very close to negative 5. So it seems like in this case, we are going to be converging to a limit. We do have a limit. It does exist, and it's equal to negative 5 in this case, or it seems to be equal to negative 5. However, this is not equal to our other single-sided limit. So these two, they both exist. These both exist, but they aren't equal to each other. So we can't say that the total limit is going to exist. So we can say that this right over here does not exist. And because of the single-sided limits not agreeing with each other, we can say that because these two don't agree with each other, we can say that perhaps there may be, we aren't exactly certain, we have to actually look at the graph to determine this, but we can see that there may be a jump discontinuity at this point. And, again, this is kind of just an inference, a bit of an assumption based on the information we're given. It's not like we're actually given the graph of the function or it's an equation, but, just based on the information in the table, we can kind of assume that this is how the function will behave. It will have a jump discontinuity at x equals 2. This final example over here, we're given this arbitrary function h of x, and we're asked to find the total limit as x approaches negative 1. And then, again, same approach. This is getting, we're just going to look at the single-sided limits yet again. Or this is not f of x anymore. This is h of x. And then the other single-sided limit. So we're going to have from values greater than negative 1. And this is a third case that we have to kind of look into, because this one's also pretty interesting. So we can look over here. Again, we have these different step sizes. We have h of negative 1 is going to be undefined. So then we can kind of look at the values that are close to negative 1. We can kind of look at like the neighborhood of negative 1, if you want to call it that. We can see over here negative 1.1, negative 1.001, and then this number over here that gets very close to negative 1. If we look at the corresponding h of x values, it seems like we're kind of getting pretty large here. We have, for an h of negative 1.1, we have negative 100, and then we have negative 1 times 10 to the 6, and then negative 1 times 10 to the 10th. So it seems that we're becoming our magnitude is growing significantly, but it's in the negative direction. So it seems we're becoming extremely negative as x approaches negative 1 from values that are less than negative 1. So we can assume, again, just an assumption here, but we can assume that this is going to kind of diverge to negative infinity. It seems to be that we're kind of becoming infinitely negative. We're becoming very negative as x gets closer to negative 1. And then if we look in the other direction, we can kind of make the same argument. We can see over here, these different step sizes as we approach -1 from values that are just barely above -1. We can see we have 100, and then 1 times 10 to the 6th, and 1 times 10 to the 10th. So these ones are growing significantly in magnitude, however, they're growing in the positive direction. So it seems we're going to be growing kind of infinitely large in the positive direction. So it seems that we're going to diverge to positive infinity. And so here we have two limits at infinity. The single-sided limits are at infinity. We don't know what this function looks like, however, we can maybe assume, based on this, there's going to be a vertical asymptote. A vertical asymptote. And, I mean, that would be a pretty reasonable assumption, because generally when you have limits, whenever a is not equal to plus or minus infinity, but you end up with a limit that is equal to plus or minus infinity, then you may be able to assume that there's going to be an asymptote, because, again, we don't know what the function looks like, but maybe we can assume, perhaps, that it will look something like this. Maybe, I don't know why that didn't become a nice line. Maybe it will look something like this, it will diverge to negative infinity, and then in this case over here, it will diverge to positive infinity, right? And then that will be our asymptote. And so we can say in this case that this does not exist either, and that is mainly because we have kind of the single-sided limits not agreeing with each other. So these are the different cases, and this is kind of how we can determine limits based on information given in a table, even when the function evaluated at that particular point is undefined. We can solve, like we saw in this particular case, that we can still, in certain cases, find a limit.